Good morning friend and welcome back to your favorite technical channel AVM Tech Android. Today I am available with the fifth video lecture related to heat transfer by means of radiation. This is the QR code of my channel and the YouTube channel name is AVM Tech Android. So either you can scan this QR code and you can enter into the channel, or you can write AVM Tech Android in the YouTube and you can subscribe this channel and you can enjoy all the free videos related to mechanical engineering. So in this fifth video lecture we are going to discuss about heat exchange between a real surface, or we are talking about heat exchange between non-black bodies. So in this video we are going to discuss about heat exchange between non-black bodies or real bodies. All the figures which you can see that we have to discuss in the present video. So first we will discuss about this figure, that is heat exchange between two non-black bodies. Then we will discuss about heat exchange between real bodies, and then we will discuss about the different terms derived for the electrical analogy. The book which I am using at present is by Heat Transfer by Dr. A.V. Mehta and Professor P.G. Choksi from Books India publication. You can also refer this book and you can go through this chapter from this book. So without wasting the time, let's start with the heat exchange between non-black bodies. So till the previous topic we were discussing about the black body. The black body is a hypothetical body and that is serve as a standard for the performance of the real body. But when we will talk about non-black body or real body, in that case what happens? Absorptivity that is not equals to emissivity, or that is not equals to 1. It means that the radiant energy that is reflected from one body to another body, some amount of heat is absorbed and some is reflected. For the real bodies, transmittivity is 0, so absorptivity plus you can say reflectivity, that is equals to 1 for the opaque body. So what happens here is all the radiant energy that will fall, that will not absorb, some amount of energy that will be absorbed and remaining will be reflected. So when we want to go for such kind of cases, we have to go for such cases with certain assumption. These assumptions are, you can find here ABC. The first assumption is each surface of the enclosure is characterized by the uniform irradiation and radiosity, that is irradiation G, and we are talking about G and J, that is irradiation and radiosity. Next thing which is there, that is each surface in an enclosure is diffused, opaque and gray. So when we talk about opaque body, I told transmittivity that is 0, tau is 0 in this case, and each surface of enclosure is isothermal, means temperature of that enclosure remains same throughout. So we will start with the first theory, that is heat exchange between two infinite parallel planes of a non-black body. So here you find plane 1 and plane 2. So you can say plane 1 is with area A1, energy emitted is E1, absorptivity is alpha 1, temperature is T1. In the similar way for the plane 2, area is A2, energy emitted is, you can say, E2, absorptivity is alpha 2, temperature is T2, and so on. So now what we had discussed for the real body, we have to apply here and we have to go for the analysis. So we start with this analysis. You can say from plane 1, energy E1 is emitted, or that is moving towards the plane B. Now plane 2 is not a black body, so it will not absorb all the radiant energy. What it will absorb is alpha 2 into E1. Alpha 2 is absorptivity of plane 2. So what is the radiant energy falling on it? Out of that fall energy, it will absorb only alpha 2 into E1. Alpha 2, that is absorptivity of plane 2. So alpha 2 into E1, that will be absorbed. So the remaining energy is reflected back. So what is reflected back? That is 1 minus alpha 2. That will be reflected into E1. So 1 minus alpha 2 into E1, that is the amount of energy that is reflected from plane 2 to plane 1. Now when it is reached to plane 1, again this plane 1 is not a black body, so it will not absorb all the radiant energy that is falling on it. What it will absorb? It will absorb only equals to what is absorptivity of plane 1. So it will absorb only alpha 1 into 1 minus alpha 2 into E1. So the amount of energy that will be absorbed here, that is alpha 1 into 1 minus alpha 2 into E1. So the remaining energy that will be reflected. So what is that value? That is 1 minus alpha 1, 1 minus alpha 2 into E1. Again that will be approached to the body 2. So what will be absorbed? That is alpha 2 value that will be absorbed. So alpha 2 into 1 minus alpha 1 into 1 minus alpha 2 into E1. So continuously on both the side, the energy level is decreased for this heat ray, or the heat which is exchanging between plane 1 and plane 2. So alpha 2 into 1 minus alpha 1, 1 minus alpha 2 into E1, that is the amount of energy that will be absorbed by plane 2. Again the remaining part will be reflected. So what is that value? That is 1 minus alpha 1 into 1 minus alpha 2 square into E1. So this will approach to body 1. So body 1 will absorb alpha 1 value, that is absorptivity of body 1, into this value of heat exchange, that is alpha 1 into 1 minus alpha 1, 1 minus alpha 1 square into E1. So this is the amount of energy that will be absorbed by plane 1. What is the reflected back? That is 1 minus alpha 1 square into 1 minus alpha 2 square into E1, that will be reflected. What is absorbed here? That is alpha 2 into 1 minus alpha 1 square into 1 minus alpha 2 square into E1. And this process is continue for a long time. So let us see the description. The assumption which we are making here in this analysis for two real body, that is non-absorbing medium air is observed between two non-black bodies. Shape factor is unity in each case because these are two parallel plates. So the surface 1 cannot see the surface 1 again. U-turn is not possible. So surface 1 cannot see surface 1. Surface 1 is only moving towards surface 2. Okay, it is moving towards surface 2 only. The emissivity or the emissive and reflective properties are constant. For both the surfaces, the emissive and reflective properties are constant. So what we had discussed. So now we have to discuss the amount of energy that has left the surface 1 per unit time, that is Q1. So the amount of energy that has left the surface 1 is E1. You can say this one, and so on. Okay, so you can say Q1. So we will erase this part. So Q1, that is equals to E1, that is this amount of energy E1, minus, you can say, alpha 1 into 1 minus alpha 2 into E1, that is alpha 1 into 1 minus alpha 2 into E1, plus you can say alpha 1 into 1 minus alpha 1 into 1 minus alpha 1 square into E1. So plus you can say here the third term is there, fourth term is there, and so on. So you can say it is you can say equals to E1 minus 1 minus alpha 1 E1 into alpha 1 into square bracket, you can say 1 plus 1 minus alpha 1, 1 minus alpha 2 plus 1 minus alpha 1 square, 1 minus alpha 2 square, plus so on. So you can say it is equals to 1 plus AB plus you can say a square b square plus you can say a cube b cube, and so on. So if we'll think that the value of alpha 1 and alpha 2 definitely that is less than 1, so the square of these terms is much lesser, and we can write that as, so in this square bracket the things which are available here in the square bracket, this is the terms available in the square bracket. So for all these terms we can write this according to maths, that is equals to 1 upon 1 minus alpha 1 into 1 minus alpha 2. So I can write E1 minus alpha 1 E1 into 1 minus alpha 2 divided by 1 minus alpha 1 into 1 minus alpha 2. Now what we had discussed is we are considering this is a gray body or real body, and hence for a gray body according to the Kirchhoff law we know that absorptivity that is equals to emissivity, and hence we can replace alpha by epsilon. So here all the places where alpha is there, that will be replaced by epsilon. So I can write Q1 that is equals to E1 into epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 into epsilon 2, where this epsilon, that is emissivity, 1 stand for body 1, 2 stand for body 2. So what we'll get is, in the same way if we go for exercise for body 2, you can say this is body 1, this is body 2, 1 and 2. We had initially start with, you can say E1 is energy that is leaving surface 1 and reach to surface 2, and all the analysis was observed. Now what I will do is I will start with here. E2 is the energy that is leaving the body 2 and reach to body 1. Some amount of energy that will be absorbed, the remaining will be reflected. That will be some amount is absorbed here, remaining will be reflected. Some is absorbed, reflected back, some is absorbed, reflected back, some is absorbed, and so on. Okay, so here some is absorbed. If we again repeat the exercise for surface 2 like what we did for surface 1, we will get this thing. So only the change is there here. E2 is replaced by E1, epsilon 2 is replaced by epsilon 1. So if we'll go for net flow of heat, because both side the heat exchange will be observed. So the net heat exchange is Q12, that is Q1 minus Q2. So for body 1 we had derived this thing, E1 epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 epsilon 2. And for body 2, what I told to you is simply you have to replace body 1 by 2 and epsilon 2 by 1. The rest thing is same. So we will get Q12 that is equals to E1 into epsilon 2 minus E2 into epsilon 1 divided by epsilon 1 plus epsilon 2 minus epsilon 1 into epsilon 2, where E is the total emissive power and epsilon that is emissivity. 1 and 2 number that is indicating body 1 and body 2. Now for body 1, what is the total emissive power? That is epsilon 1 into sigma into T1 power 4. That is according to the Kirchhoff law, which is known to us. And the detail for the previous lecture is available in the description box. You can refer the link and you can again go for the Kirchhoff law and you will find these formulas. Similarly for body 2, total emissive power that is epsilon 2 into sigma into T2 power 4. So that is, you can say, for body 2. So if I will go for net heat exchange between body 1 2, I will get epsilon 1 into epsilon 2 divided by epsilon 1 plus epsilon 2 minus epsilon 1 into epsilon 2 into sigma. That is Stefan-Boltzmann constant value we have to remember, that is 5.67 into 10 power minus 8 watt per meter square Kelvin power 4. Absolute temperature of body 1 power 4, absolute temperature of body 2 power 4, where this term is known as F12 or it is also known as interchange factor. So net heat exchange between two black bodies, that is equals to interchange factor F12 into sigma into T1 power 4 minus T2 power 4 for non-black body, where absorptivity that is not equals to 1. I hope this theory is very much clear to you, how we have to find out the net heat exchange between two parallel non-black bodies. Now instead of two non-parallel black bodies, if we are considering only a surface, real surface, what is the net heat exchange that we want to find out? So you can find here the opaque non-black surface is available and we want to find out what is the heat exchange between the real body. So what you will observe here is this is the amount of radiant energy that is falling on the surface. So when it is falling, there is a reflection, and what is the reflected portion? That is J, that is equals to E plus rho G. Some amount of reflected part of G plus its own emissive power. So its own emissive power plus reflected part of the energy, so that is radiosity J. So J that is equals to E plus rho G. So you can see E, or you can say epsilon, that is emissivity of the surface, EB that is total emissive power of black body, rho that is reflectivity of the surface, G that is the irradiation, J is the radiosity, unit is watt per meter square, E that is the emissive power of the non-black surface or non-black body, and Q net that is the net energy that is leaving the surface. This summation is the net energy that is leaving the surface. So what you can see is the energy which is leaving the surface, that is E plus rho G, and the amount of energy that is falling, that is G. So we know that emissivity that is E upon EB. So emissivity is the ratio of total emissive power of any body to the total emissive power of a black body, what we learned in previous videos. So I can replace this E by epsilon into EB plus rho G. Now we know that absorptivity plus reflectivity plus transmittivity that is equals to 1. And for the opaque body, we know that tau is 0. So we know that absorptivity plus reflectivity that is equals to 1, or you can say reflectivity that is 1 minus absorptivity. So what I have to do is, in this equation, in this equation, instead of reflectivity, I am putting this part. Reflectivity is 1 minus alpha. So you can see that is observed here, reflectivity is replaced by 1 minus alpha. And according to the Kirchhoff law, we know that according to the Kirchhoff law, we know that absorptivity, that is equals to emissivity. So again I am replacing this alpha by emissivity. So my equation J, that is radiosity, that is equals to epsilon into EB plus 1 minus epsilon into G. Now I am going for simplification. I am multiplying G with 1 and G with epsilon. Okay, and then what I will do, I will put this E minus EB into epsilon on other side. So what I will get, radiosity minus epsilon into EB, that is equals to G minus epsilon into G. So from that I will get G, that is irradiation, that is equals to radiosity minus emissivity into total emissive power of black body divided by 1 minus emissivity of the real surface. So what you can see, the net energy which is leaving the surface, that is J minus G. So J minus G, this G value is now known to us. What is the value of G? So what we are doing, we are going for simplification. We are multiplying this 1 minus epsilon here and we will go for simplification. So it is multiplied here, we will go for simplification here. So what you will observe, I think this JJ, that will be cancelled, this epsilon, that will be common. So what we will get, EV minus J into epsilon divided by 1 minus epsilon, that is Q net upon A. So what is Q net? That is net heat exchange in a real surface, that is EB minus J divided by 1 minus epsilon divided by epsilon into A, or you can say A into epsilon into EB minus J divided by 1 minus epsilon, where A is the area of the real surface, epsilon, that is emissivity, EB, that is total emissive power of black body, J, that is the radiosity, again epsilon is the emissivity of real surface. So if we'll talk about the real surface, what you will observe again is the heat energy that is leaving the surface 1 and reach to surface 2, like what we did for the previous case, that is J1 A1 F12, and what is reflected back from body 2, that is J2 A2 into F21, where J1, that is radiosity of body 1, area 1, that is area of body 1, F12, that is a shape factor, view factor or configuration factor. You can refer the previous video for the detail. F12 indicate the fraction of energy that is leaving surface 1 and reach to surface 2. In the similar way, this J2, A2 and F21, that is, you can say, radiosity, area and shape factor of body 2. So if we go for again net heat exchange between body 1 and 2, in that case what we will get, Q12, that is equals to J1 A1 F12 minus J2 F21, and according to this reciprocity theorem, A1 F12, that is equals to A2 F21, and because of that what we will get, this is a common, so we will get Q12, that is net heat exchange between two parallel surface is J1 minus J2 divided by 1 upon A1 F12, or you can say 1 upon A2 F21. So this is a resistance offered when we are talking about heat exchange between two parallel surfaces. Now in the next video we will discuss about electrical network analogy part. So when we know all these formulas, how the resistance will be offered, it is very easy for us to go for electrical circuit. So in the next video we will discuss about electrical network analogy, that is the alternate and easiest approach to analyze the radiation heat exchange between any surface. Very important is any surface, not two surface. We can discuss about 4, 5, 6, 7 surfaces. Either they are black surface or non-black surface. So every time we should not repeat this theory that these two bodies are there and the rays are reflected. We have to repeat the same thing for another body and so on. If we go for electrical analogy, it is alternate simplest approach. So in the next video we will discuss about this simple approach where 1 minus epsilon divided by A epsilon is known as the surface resistance and 1 upon A1 F12 is known as a space resistance. So this surface resistance is depend or it is related to the surface property of radiating body, whereas the space resistance is related to the distance and geometry of the radiating body. So when we have to discuss about radiation heat exchange between two body, what are the number of resistance offered? First is the surface resistance of body 1, surface resistance of body 2 and the space resistance. So total 3 resistance are offered in this case when we will talk about two body network. So in next turn we will discuss in detail again about this part, electrical network analogy part, and we will try to solve some simple as well as complicated problems related to radiant heat exchange between two black or non-black bodies. The surfaces are two or more than two. So we had discussed a very important thing, what is the space resistance and surface resistance in case of radiation heat exchange. So if you like this video, then do not forget to subscribe this channel and also do not forget to share this channel among your friends, among all the needy engineers. Thank you very much.